I mentioned in a previous video that when I was hooking up the simplest VGA project to the Benita 6502, and when I synchronized the clocks together, I used a bunch of hand-drawn diagrams to help me figure out how to synchronize them and how to organize them. And over on Reddit, a guy called Eric Badger asked for more details on that. He wanted to see the diagrams and to see how I'd worked it all out. So this video is all about that. This is going to be a bit more theoretical than most of the stuff I've done, which is usually more practical, so let me know if you like this kind of thing. But I'm going to try and keep it quite light here. Again, also, if you would like even more detail on this, then I can certainly do something more in depth and a little bit more sort of explanatory. Anyway, to begin with, here's the general system diagram of the architecture of these two things joined together. I haven't really drawn much on in the sort of CPU side. All of the CPU address and data buses in the actual computer obviously also go to the ROM and the RAM. I didn't put that on here. This sort of portion at the top here is the simplest VGA project, and this bit here is the sort of new bit that hooks the CPU up. So in a nutshell, we have some form of clock up here. It's driving a couple of 8-bit counters which provide an address to the video RAM. The video RAM data output goes through a D flip-flop, and the same clock circuit up here is also clocking that D flip-flop. It's doing that once every 16 VGA pixels. And when it clocks that in, the D flip-flop starts to output whatever data it was receiving from the RAM at the time to the VGA connector. And one of the signals from the D flip-flop is also used to reset the counters. And that was the gist of the simplest VGA circuit. And then on top of that we have the CPU down here. The CPU's address bus comes through these D flip-flops to sort of interface it onto what I'm calling the video address bus. And the CPU's data bus goes through a D flip-flop down here to interface it onto the video data bus. Now on this diagram I put D flip-flops in these places. That's not actually how I built the circuit in the end. I used bus transceivers instead, but the logic's still the same. The critical thing is for this video address bus up here, we have a bunch of devices that can drive that bus, and they all have an output enable signal, so they don't all drive it at once. Either these two are driving it or these two are driving it, and then the video RAM gets its address from there. And then again down here on the video data bus, either the video RAM is writing to the data bus, or the CPU's D flip-flop down here is writing to the data bus, and I need to arrange things so that only one of those happens at a time. So in terms of organising this and making these two things cooperate well together, it's all about orchestrating how certain control signals happen in relation to each other. And the obvious ones are the output enable on these two counters, the output enable on these 3 bus drivers here, and the write enable versus output enable on the video RAM. Those are the signals we kind of need to generate now, and on top of that we have to work out how to generate them in relation to the clock that increments the counters and the clock that latches the D flip-flop, and also the core clock of the 6502, which is called Phi2. And we need to make sure that the 6502 isn't trying to write this at the same time that the video circuit needs to latch the D flip-flop, because this is really non-negotiable. The D flip-flop has to get latched at a constant rate in order to keep the image on the screen stable. And that's obviously why the image wasn't stable at all when I didn't bother with this bit. So the key thing that we're going to need to do is really to synchronize the Phi2 input to the CPU to happen at a good time for the video circuit. I did a whole diagram for the kind of CPU timing here. This was actually for the first version of this, which didn't have the CPU synchronized with the with the video circuit clock. This was more about how the CPU itself works with relation to the video RAM. It was still kind of relevant even after the change, but this was really the first version of the circuit where the video display would blank out whenever the CPU wrote to video RAM. So you can see the kind of timing diagram I draw up here, which is basically the same kind of thing you find in a datasheet. Phi2 up here is obviously the CPU's system clock. Let's get closer to that. So Phi2 up here is the CPU's system clock. Our W bar is the read not write signal from the CPU. So this is kind of an input to the CPU. This is an output from the CPU. And when Phi2 is low, the CPU kind of sets the read not write signal along with all the address lines at this stage. And at that point we can work out what kind of bus access it wants to do during the Phi2 high period. And based on that, we have this sort of ROM chip select line, which is going to go low because this is a write to the sort of ROM area of memory of the memory map. So the ROM chip select will go low at this point. And what we really need to do is make sure that the counter output enable. So this is the output enable on the counters that drive the video address bus. We need to make sure that that output enable signal goes high in response to that kind of set of conditions there, which is not hard to organise. And then we have the video RAM write enable signal down here, which needs to dip down low, at least for the very end of Phi2. That's the important point when that needs to come low. I've put it low throughout Phi2 there, which is fine as long as there's enough delay from this point to this point. Because at the same time as these counters being disabled, I actually enable the, well, what I call the D flip-flops on the other page, but they're actually bus transceivers. So it's at this point really that the video RAM address bus switches from showing the value of the counters to showing the value the CPU wants, and we need to leave a little bit of time before we enable the writing to the video RAM, otherwise it will scribble over the wrong addresses. And then there was kind of this circuit, this sort of boiled down logic gates version of that, is how do we work out the counter output enable and the video RAM write enable signals from these kind of inputs. And well, there's a few variations on that, but I basically tried to refactor the circuit to simplify it and replace the NOR gate with AND gates, for example. I inverted that AND gate here, and then I wanted to combine the inverters and the AND gates by using NAND gates instead, so I ended up with this circuit down here, not the bottom one. The next one up is the one I actually used. And you can see, that the inverting of the read not write line is done by a NAND gate, and we actually have a ROM output enable that comes from that, because it's pretty important that the ROM only outputs during a read cycle after this change, which wasn't how Ben had set up in his original design. So yeah, that kind of feeds through, and we end up with this ROM output enable, a latch output enable, which really means the bus transceivers, counter output enable, and video RAM write enable. And those are the key signals that we actually need to generate. Like I said, this whole page was about the version that didn't have the CPU clock synchronized. It was all about just how to choose when to disable the video circuit when the CPU wanted to write. The next page is all about the synchronization aspect, which is what Eric was actually asking about. So let's start at the top here. Actually, I'll give a shot of the whole page first in case you want to study it in any detail at some point, but I will go through everything and explain it. So this section at the top, the very top line up here, is the 25.175 MHz clock. This is a crystal oscillator. I've only drawn here the rising edges of it. I didn't bother with the whole waveform, so every tick I put there represents a rising edge on that clock. That clock then drives a 4-bit counter, and these are the 4-bit outputs from that 4-bit counter. So, one of them goes at half the clock rate, the next one down goes at half that rate, and so on. It's just a frequency divider, really. And right at the start here, I've got them all equal to 0, and then there are like 16 ticks of the main clock before they're all equal to 0 again, and they're counting up in binary. If you want to view them as a binary number, they're counting up 0, 1, 2, 3, 4, and so on, all the way up. At the bottom here, there's a terminal count output, which also comes from that chip. It's a 74HCT163, I think. And the terminal count output simply marks the very last count before the whole thing wraps around. And that's usually used for chaining counters together so that you can signal that the next counter in line should increment at this stage or on the next tick, the next counter should increment. But I actually used that as a convenient kind of data signal to drive some of the video circuit. So this cycle of 16 ticks of the main clock represents one actual pixel in my original simplest VGA implementation. It's not exactly the case anymore because I've increased that horizontal resolution in my latest versions, but let's stick to that version for now because that's the version I was originally setting this up for. And basically during that 16 clock cycle, I needed to orchestrate two particular events. The first one was triggered by the terminal count here, and that's the one I've marked as tick, and that's when the 8-bit counters get their tick signal so that they increment to the next value. They actually don't put that out on their data outputs until the next cycle, so I mark that separately here. But that's driven by the terminal count input there. So the rising edge of the terminal count causes the 8-bit counters to tick. No, this is not this 4-bit counter. That's separate. There are 8-bit counters that are driven by that signal, and those 8-bit counters are the ones that go into the video RAM address. Aside from that, the other important point is this point I've marked as latch, and there's another one over here for the next cycle. And this is the point at which the D flip-flop latches in new data from the ROM or video RAM. And this is the point where it is really critical that the CPU is not doing anything with the video RAM bus, or with the video address bus or the video data bus, because this is the point at which the video circuit absolutely needs that bus to be clear for it to latch in that data. Once that data is latched in, it doesn't really matter what happens on the bus here until the next latching point over there. The D flip-flop has a certain hold requirement, so after it latches you need to keep the data that it was reading valid for a short amount of time. It's a pretty short amount of time for a D flip-flop. At the same time, you need to also have that data ready ahead of time. That's a little bit of a longer time generally, but it's not a super long time, so we're not really pressed for this, so long as the region around this latching point is relatively clear of the CPU being on the bus. So then the trick is working out how can we fit the CPU into this picture. Where can we put the Phi2 signal so that it doesn't collide with particularly with these latch points that I've marked there. As on the previous page, the important point during the Phi2 signal is really the point when it's high. That's the point when the CPU really wants to be driving the buses. It's a little more complex than that. It's really the end of the Phi2 being high that's most important that the CPU has bus access for, but simply speaking, it's best if you just organise for the whole of the Phi2 period for the CPU to have access to the bus. So the first thing I wanted to do, I suppose I should note here as well, because these counter outputs are essentially dividing that main clock frequency by 2 each time, I just marked the frequencies on underneath them here for reference. And the first and easiest way to synchronize the CPU into this picture is just to take this bottom one here, the 1.57 MHz signal, and say that we're going to try and use that for our CPU clock. We're going to try and make our CPU run at 1.57 MHz. That's simple because that's actually the same rate that the latching is happening, and basically what it means is that we need the Phi2 signal to be low around the period of the latch, and then go high, and it can stay high for quite a while until the next latch, when it needs to come low a certain amount before the next latching time. And that's kind of what I've drawn down here in this synchronous 1.5 MHz section. You can see I changed my mind quite a bit about exactly where I wanted that Phi2 signal to be, but you can see it right at the top. Here's the Phi2. I've drawn it starting high, falling low. The lines I drew down from the latch were to make it easy to see where that was in these later diagrams. So that's coming down low nice and early before the latching point, and then there was a couple of points here where I considered it could go up again, and then it would stay up for a while and then go down again. I didn't draw it very symmetrically here. It ought to be a symmetrical signal. So how can we make Phi2 actually be that shape? We have a nice 1.57 megahertz signal up here, but it's got the wrong phase. It goes up and down at the wrong times. The thing I figured out to do for this, I figured this out a while ago. It's probably a very standard technique because it's very effective. You can take any clock signal you want and delay it until the rising edge of a different clock signal by simply using a D flip-flop. And what you do is you take the D flip-flop and you arrange for the D flip-flop to be clocked by the higher frequency signal, and on every rising edge of the higher frequency signal you make it sample the lower frequency signal. So for example, if we were to sample D3 on the rising edges of D2, then think about what that means. At the start, you don't really know what state it would be at the start, so don't worry about that for now, but here's the rising edge of D2. At this point D3 is low, so our sampled signal would be low at this stage. The next rising edge of D2 is over here. At this point D3 is high, so at this point our signal would go high. And then it will stay high until the next rising edge of D2, at which point D3 is now low and it would drop down low again. So what we'd get would be a signal that would fall down here, it would stay low, then it would go high, and then it would stay high, and it would go low. And I hope you can see it's the same signal as D3, but it's been delayed by that sort of half period. It's a quarter of its entire wavelength actually, but it's delayed so that its rising edge has basically been delayed until the next rising edge of D2, and its falling edge has been delayed until the next rising edge of D2. And the first diagram I drew down here had the rising edge here corresponding with D2 going up here, because I was thinking of clocking this on D2, which would have lasted until here. I don't recall exactly why, but I decided I wanted to clock it on D1 instead. And that works in exactly the same way. It might not be quite as obvious because, I mean, D2 rises here and the signal would go down, and it rises here and the signal would go up. That kind of makes sense. D1 rises too many times, but that's okay. Basically what happens if we clock with D1 is this rising edge of D3 gets delayed until the next rising edge of D1, which is sort of half the amount it would have been delayed before. This next rising edge of D1, D3 is still high, so it actually has no effect on the output signal. And then this next rising edge of D1 is the one which brings it low again. So clocking it based on D2 delays it by the duration of D2 being low, pretty much, and clocking it based on D1 delays it by the duration of D1 being low. So picking a different one of these higher frequency clocks allows you to shift it by more or less. The one thing you can't do easily is shift it the wrong way. You know, the most you can shift it is about half this way. You can't really shift it more with a single D flip-flop. Anyway, that's the basic technique, and what I figured I would do down here is take D3 at D1. That's just a notation I used for the D flip-flop, sampling D3 on the rising edges of D1, and it gives this waveform here. Actually, that one's in the wrong place, but never mind. It should be over here. But it gives this sort of slightly earlier one here I drew in. Then next I looked at the counter output enable signal. And I figured this could be just the same as the Phi2 signal. I didn't draw it exactly like that, but basically, particularly during this write cycle, we want the counter enable to be low around the latching points. That's the critical stage for the counter enable signal, because the counter enable signal is the one which puts the right address on the video memory bus for the video system to latch in here. So the only thing that matters for this signal is that it's low at this point and high when the CPU needs access to the bus, and the CPU needs access to the bus basically when Phi2 is high. So this entire signal can just be set the same as Phi2. Next one we have down here is latch output enable, and this one, it looks a bit like the inverse of the counter output enable, but I don't think I implemented it like that actually. I think I did something a little bit more sophisticated for that, and I made it only dip down when the CPU was actually writing to the bus. Didn't matter very much, but I mean it mattered because I also used it to work out the video RAM write enable. But basically this ends up meaning this one should be low when phi2 is high and it's a write cycle and it's writing to video memory. If all those are true, then this signal dips down along with phi2. And that's actually calculated using the old VRAM write enable calculation from the previous page. Is that circuit of NAND gates is basically what I used to calculate that in the end. Next down is the VRAM write enable signal, and this one has changed a bit. The reason for this is that we need to not start writing to video RAM until a certain amount of time has passed since the counters and the latches swapped conditions here. If we start writing straight away, then the address won't have settled properly here, and the video RAM won't be ready for the write. So we need to make sure we delay long enough here. And again, you can check the data sheets to work that out. Yeah, I've just sort of put something in here. I don't think I was particularly careful about how long I waited. I just put something in and made sure it works. But you really ought to check the data sheets for that kind of thing. And this is again implemented using a D flip-flop. So the way I wrote this here is it's the latch signal sampled at D2, but set by D3. So that means that we're looking at this latch signal up here, and this one is going to copy that one every time D2 rises. Now D2 rises here, which we're not very interested in, and here. So at this point, this signal is copying the one above it and falling down because this one is low at that stage. And then it would copy it again, over here. It's basically again phase shifting that signal by the sort of half period of D2, except that I have marked it to be set by D3, and what that means is that any time D3 is low, this signal is forced high regardless of whatever else it was doing. That's the way D flip-flops work. If you connect their set or reset input to something else, it's an asynchronous set or reset, and it will just push them into that state. So what that means is that although it does fall down here, and it can do that because D3 is high, when D3 next falls low again, this just gets pushed back up again. So there's a little notch of writing going on here. But yeah, that was about it for the 1.5 megahertz case. That all worked very well. And so from there I looked into how I could increase the frequency. So the next obvious one is just to double it up to 3.149 megahertz, making it essentially copy D2 instead of D3, and that's what I did down here. So this is the 3 megahertz version, I called it here. It's 3.149 really. This is arranged a little bit differently to the one above. What I've written here is the inverse of phi2 being D2 sampled at D1. And the reason for it being the inverse is because if it wasn't the inverse, it would just be in the wrong condition at this latching point. Remember that at the latching point, we need phi2 to be low. And sampling D2 at the rising edges of D1 actually leads to a signal which is high at that point. So I just calculate that signal, but I use the inverted output of the latch, the inverted output of the flip-flop to drive phi2. And that all works well. The counter output enable is still the same as phi2, i.e. the same as the inverse of the one above, so I've drawn that here just to make it clearer. Latch output enable again works exactly the same way as before. It's just a copy of the old VRAM write enable circuit from the previous page. So that stays high and then dips down during the write cycle, which I've put in here. And the VRAM write enable now is once again the latch output enable, but instead of being sampled by D2, I've got it sampled by D0 here, and set by D1 instead of being set by D3, and that causes again a little notch to appear here. It's long enough after this edge here for the address bus and the the address bus and the RAM to be ready to provide the data that the latch needs. For the address bus and the RAM to be ready to accept the write without scribbling on other areas of RAM. I could have delayed it quite a bit throughout this process, but yeah. But that's that. There is a little bit more to this one though, because I've drawn the write cycle over here. The write cycle could very well have occurred over here as well. But it's not a big deal, it would just be exactly the same thing, but appearing over here, and because phi2 falls well before this latching point, that's absolutely fine as well. The RAM has time to get back into video RAM mode for the latching point after this cycle. So that worked really well. The next thing I wanted to try was doubling it again to 6.3 megahertz. I can't remember what it is, something like that. It's over 6, I just wrote 6 here. I had 2 goes at that. This first one here was, I guess I had the inverted phi2 as D1 sampled at D0, and the rest of it was basically the same. I don't know. I think what I found here was it was really hard to find a good way of doing the video RAM write enable, because I have these. I have this kind of period here, and I would need the video RAM write enable to kind of be active at the right point here. And I think what I found when I looked up at the clock signals was that there wasn't really anything really convenient to calculate that from there. So instead I had a second go at that one, and I did it a little bit differently. I have phi2 here is being driven by a D flip-flop sampling from D1. That's the 6.29 megahertz line up here. So we're sampling D1 on the inverse of the input clock. So I had to actually feed the input clock through an inverter to do that, because it's just a crystal oscillator, it doesn't provide its own inverted output. So that means that although I've drawn all the rising edges of the clock here, it's actually the falling edges of this clock signal that I was inverting to cause rising edges on the D flip-flop and sampled the D1. And what that meant was that this entire D1 signal moves half a square to the right. And that'll be what I've drawn down here. You'll see that this phi2 signal is not aligned with the grid anymore, it's half a square off. And that was so that on this latching point here, where this dotted line is, I needed to make sure that phi2 was actually high during this latching point. I need to make sure that phi2 was low during the latching point, but this is the inverted phi2 signal we're seeing here. So this signal needs to be high during that latching point, because that's when the video circuit needs to be reading from the video RAM. Remember I said before that the end of the phi2 period is the most important in terms of writing in particular, but also for reading. That's the point where the content of the data bus is really critical. The start of the phi2 being high is not so important. It's really the end of that signal that's the point where the magic happens. So that's partly why I've shifted it like this and arranged for it to overlap in this way. The end of the signal, stuff happens, there's a hold time after the stuff happens, and we need to make sure that hold time doesn't collide with this latching point either. So I didn't want to shift it too much across. That's probably more why I didn't do it this way actually. I didn't really think about that, but I was probably concerned that the end of the phi2 being high here was going to be too close to the latching point. It might not have worked. I can't remember if I even tried that one. I don't think I did, because I didn't draw the write enable line on it. But yeah, I did it. What I've tried to do here is basically arrange that these little write notches are evenly balanced around that dotted line, because that's what really matters. Those write notches need to be pretty evenly balanced around that dotted line. The rest of the calculation here is pretty much the same as before. This one was also a little bit tricky to do. It's the LOE line, the latch output enable line, sampled at the inverted clock, same as this one is sampled at the inverted clock, and then set by the inverted D1. I can't remember how I worked that out, but it was just whatever gave me a nice little notch at the right point here. So yeah, that's about it. So this is quite a long and theoretical one. I guess you can see that I wasn't particularly rigorous with the way I worked this out. I didn't spend a lot of time looking at the actual timings in the datasheet. And honestly, I didn't expect the 6 MHz one to work, given that I hadn't really thought it through as well as I probably should have done. But this is the method I use, drawing the diagrams, thinking about these points where it's important that the video circuit has access to the buses, trying to work out how to time these signals so that the CPU is doing its action between those critical points instead of colliding with them. And like I said, the technique of using a D flip-flop to take a signal that's at the right frequency and phase shift it, that's a really powerful one. I use that a lot, and it works very well. The only thing I'd say is be careful not to do it in such a way that the rising edge you're using to sample coincides with any form of change in the signal you're sampling from. You need to make sure that the signal that's being sampled is held stable at the point of the rising edge occurring. So for example, up here, if I was trying to use the clock signal as the higher frequency sampling clock, that just wouldn't work, because this clock signal is rising at the same point that all of these other ones are changing. So if I took D3 and sampled it with that high frequency clock there, it would be trying to sample D3 at the very instant that it's actually changing state, and you don't want to be doing that. And again, that's why I inverted the clock, so that I was sampling halfway between these lines, and that was long enough after state changes for it to not cause problems. Anyway, I hope that's interesting. It's just an example of some of the kinds of notes that I drew while making this. I mean, there were others as well. There's some diagrams thinking about resolutions and things like that. Different ways of hooking timers up. This is what I've actually put in at the moment, but it doesn't work very well. I have to take it out again soon. But yeah, I take these kinds of notes from time to time, usually when I want to think about the circuit without actually working on the circuit. And yeah, I find them very useful. So again, let me know what you think. This was a much more theoretical kind of video than usual. I'd be interested to know if you guys like that, because I can certainly do these kinds of deep dives into more things. And like I said, I didn't really cover this in a lot of detail. If you do want more information about how that all works, I could do another one of these with much more info on that. Just let me know what you like.